Hello, welcome to our lesson on optimization. The book names this section something a little different. I think it's applications of extrema, something like that. But that's what this is, optimization. That's finding a maximum of something, finding a minimum of something. And in particular, we're talking about word problems. So these are word problems where we're finding max or mins. That's optimization. So this isn't material that's super new, but we are laying things out a little differently given this word problem context. We want to follow these steps. So first, almost seems like I shouldn't have to say this, but we do want to stop and think about this. We want to read through the problem carefully, and making sure we're searching for the right things, making sure we understand everything. And we want to understand, wow, I missed a lot there. Understand what is given to us and what is unknown. That's what we have to figure out. Step 2, and we don't do this every time, but if possible, or if it's helpful, draw a picture. I'd say usually for financial problems, we don't do this. But if you're trying to, if you're doing a geometric problem, which will be our first example in a bit, then it usually helps to draw a picture. Number 3, an underrated step here. Well, especially this first part is underrated. Describe which variable must be optimized. So which thing am I trying to maximize, or which thing am I trying to minimize? That's the main function we're going to be focusing on. And then we express it in terms of one variable. Underline that one. Because, at least at this point, and well, for the whole course, we can only take the derivative of a function with one variable. If you take Calc 3, then you get into a little more than that, but we're of course not doing that in this class. So we need everything in terms of one variable. Number 4, a step that could be overlooked often, but maybe we shouldn't. Find the domain of the function. Excuse me. Of this function from step 3. And well, the reason I say this is because we may have certain endpoints which we will then need to check as critical points for finding a maximum or minimum. So step 5, that's step 5, is find the critical numbers. These are the candidates for maximums and minimums. For the function, and we classify the critical points as maximum or minimum. Okay. And this is what I was saying a bit ago. We check endpoints if applicable. So that comes from the domain, step 4. And then number 6, we're pretty much done at that point, but we want to make sure we give our answer in the appropriate form. I suppose I didn't write this, but in step 5, we may sometimes need to check that our critical points are truly a maximum or truly a minimum. And we'll see a bit of that later. Okay, so now for the rest of the time, the plan is to do 3 example problems. So first, a geometry problem. We want to find the maximum area we're trying to build a fence, and we have a certain number of fencing, or a certain length, I should say, available to us, and we want to maximize that area of our little pasture. So find the maximum area we can enclose using 400 feet of fencing. And this will be, of course, in the shape of a rectangle. Keeps the problem a little simpler. So we know we want a rectangular pasture, and we have 400 feet of fencing to work with. And so based on that knowledge, we want to find the maximum area that we can. Okay. And I'm going to add a little something else. Makes the problem a little more interesting. Let's say one of the sides we don't need to use fencing. So this is where one side doesn't need fencing. And that will be because of a river. And I will add some extra information. The river is across from the longest side. So it runs parallel to the longest side. Assuming that we don't have all equal sides. But I suppose that is a possibility. We'll see that we don't get that. But here's the picture, or let's follow our steps in order, shall we? That's step 2. Step 1. I won't keep scrolling up every time, but for step 1, we want to read through the problem carefully. I think I've already kind of done that, explained it pretty well. We want to understand what is given and what's unknown. So maybe we'll start there before we start drawing. So what information is given to us and what is unknown? I'm especially talking about the variables involved. So what's given is the perimeter of this enclosed area, because that's the length of fencing. And let's call it capital P. Perimeter is 400 feet. Then what's unknown to us? Well, pretty much everything else. The area, and that involves both the width and the length. So I'll go ahead and write all 3. let's label these as such. I'm going to call the width X, even though you could just as well call it W, but I'll just call it X. Doesn't matter too much as long as you're consistent with your notation. When it comes to, say, a quiz, for instance, or something like that, you'll just want to be clear with your labeling of things and then be consistent with your choice of letters. Okay, so picture, why don't we get a nice blue river going here? Oh, and the reason I chose X, by the way, for width is because that's what, there's a similar homework problem to this, and I'm sticking with their language, so it's easier for you to deal with when you encounter it. Okay, length is an L. Okay, so the picture looks like this. Nice rectangular shape. We don't need fencing on the side across from this length, L. Step 3. We want to decide which variable is being optimized here. Which of these things we're trying to optimize. Well, I'm trying to maximize area. That's the goal. So area will be our main focus. So we're maximizing area, which is the length times the width, or excuse me, X, I called it. Well, remember up above, I said I want it in terms of one variable. That's important because we only have tools to deal with that. So right now I've got two variables, length and width. But what comes to our rescue is that we can express one of them in terms of the other. It'll be easiest, I think, to express L in terms of X, so that we'll just have a function of X. So we need that in terms of one variable. Well, what's given to us, that's usually what comes in handy at this step. We know the perimeter is 400 feet. So P, which is 2x, because x plus x, plus L, and remember there is no other side, so just a single L, is 400 feet. And if I just rearrange things a little bit, subtract 2x from both of these sides here, well, now I have L as a function of x. L must be 400 minus x, or 2x, sorry. Let's fix that. There we go. All right, so making this substitution, now this means that A is 400 minus 2x times x. Now it's just a function of x. So in fact, I may even change the name to A of x, area as a function of x. Let's go ahead and maybe simplify a little bit. Multiplying that x. So now we're done with step 3. We found what we're trying to maximize, that's area, and we've expressed it in terms of one variable, just x. Now, before we start finding critical numbers, it's helpful to find the domain first, because if you have endpoints, like a closed interval, then those endpoints will be critical points. So we'll want to find them first. So the domain All right, well, again, we're just in terms of x now, so we're thinking about x values that are allowed. What's the smallest x value that is even possible? Well, that would be 0. Well, even that is not very practical, but we'll just go ahead and call that an endpoint. It's almost certainly not going to give us the maximum area, right? Because if this is 0, then we'll be squished to just a length along that river, and that's actually 0 area. So this is like an extreme case. That's usually how these go. What's the maximum that x can be theoretically? Well, that would be when length is 0. That's like the opposite limit. If the length is 0, then these sides would be smushed together. Or I guess maybe I'll draw it like this, like they would go in towards each other if L is 0. And you would end up with just a straight line. Also not very practical, but it is our rightmost bound of what x can be. Okay, so to figure that out, it could be a little confusing because, right, if L is 0 and these sides then come in together, we would have a straight line that's perpendicular to the river. Would I use 2x for my formula? Or just x because it would be one line? By the way, I wouldn't sweat this too much because, again, that's going to give us 0 area, but let's just do this exercise. So the way to solve that little dilemma, well, think about the limit as L goes to 0. A limit tells you what's happening as you get closer, 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 closer to this reality of L being 0. And so that'll give us a very clean mathematical picture of what to do. So, what will the perimeter become? Will it just be x, since the lines would technically merge together, or 2x? Taking care of this limit will solve that problem for us. Again, don't worry about this too much. It's a little complicated. I'm going to go ahead and finish this. So this would give us the perimeter is 2x plus L, right? And L is going to 0, so it is indeed the 2x problem. So that's what the perimeter, the fencing, becomes when the length goes to 0. And now we set this equal to 400 because that is our set perimeter. And then we can solve for x. X is 200. So this was a very long way of confirming that the longest x can be is 200. Okay, but again, that we know for sure that's not going to be our answer anyway, because that'll give us 0 area. We're trying to maximize area. But it's just a helpful exercise, I think. Okay, so that was step 4. Step 5 is to classify our critical numbers. Well, we need to find them too. We've just found 2 of them, these endpoints. And the other one comes from, well, when the derivative is maybe undefined, that doesn't happen in this case, or 0. Well, I should be underlining this thing. When is this 0? Let's find that derivative real quick. Ends up being pretty straightforward. Set it equal to 0. And you get 4x equals 400 or x equals 100. So that's the width of the fence that gives us a critical number. So a of x is a continuous function on a closed interval. So I can use extreme value theorem that tells me that an absolute maximum must exist on here. And that's our goal. Well, since we know it must exist, it must be at one of these critical points. So we take our x in our area function and plug in the critical numbers and see what we get. Well, those extreme cases of 0 and 200, that'll be where one of the fence side lengths is 0. That'll give us a 0 area. But then when you plug in 100, you get 400 times 100. This will almost certainly be the right answer. Minus 2 times 100 squared. That's 40,000 minus 20,000. Okay, so 20,000. And now we get to the end of the problem. So this is clearly the biggest number. So that'll be our absolute maximum. So the step 6 I gave was give the answer in appropriate form. So we have to find what in particular is the problem asking about. And we also want proper units as well. So it says to find the area. So not the width that gives the maximum area, not the length that gives the maximum area, but we're saying find the area itself. Okay, so that's helpful. That means it'll be this 20,000 number we just found, but we also want proper units. So the maximum area is 20,000, and the length of the fence was given in terms of feet. So this will be feet squared for area. Okay, and we also know the dimensions of the fence that give us this, but the question isn't asking about that, so I omit it. So that's a nice geometry problem. Let's do a financial problem. This is also a similar problem to what's in the homework. I feel like the wording could be a tad confusing. That's why I'm going over this. So let's say we have a local club is arranging a flight to Hawaii. And let's say the cost for this flight is $560 each for 81 passengers. But what if we exceed that number? Well, then we start getting a discount in the form of a refund. So this is with a refund of $5 per passenger for each passenger in excess of this 81 number. Then the question, our task is to find the number of passengers which will maximize revenue the revenue received from the flight. Or you could just as well give this from a different perspective and talk about the cost and minimizing cost for the passengers. But that's ultimately the same thing. I think it helps. I think it's easiest to do it this way because it allows us to think of this 560 number in a positive sense. And I'm following the example that Pearson gives. Okay, I personally found this wording a little confusing at first. So technically, the 560 number is being applied to everyone, even beyond these 81 passengers. It's just that once you go over that 81 number, then this discount comes into effect, which will affect everybody's price. This is per passenger. All right, so I'd say we're really only dealing with unknowns. Not a whole lot is given besides the formula for how this works. But it's not like we have a given number of passengers for certain. That's what we're trying to figure out, really. So not really a whole lot of variables involved in this anyway. So yeah, this is the main thing, the number of passengers. P. Well, the other important thing is revenue, which is also an unknown. Let's call it R. You could technically add the refund as well. I'd say you don't necessarily have to write that at this point, but whatever works for helping you solve the problem. All right, so I meant to, not that it's a big deal, but I think I'm going to use a lowercase. So the revenue, R. I'm not going to do my step 2, drawing a picture here, because it's not very useful for financial problems like this. So now I'm trying to find the thing I'm trying to optimize. In this case, we're trying to maximize revenue. So R is my main function I'm looking for. And we need it in terms of one variable, that variable being the number of passengers. So the revenue, well, at first it'll be this 560 number for each passenger. So 560 times P. But that's before the refund comes into effect. So for now, I'm just going to say minus refund. Just thinking of that as one quantity, the total refund for the group. Now let's find that refund part. We need it to be in terms of P, so that we have R as a function of just P. Well, we were given, there's a refund of $5 per passenger, so I'm multiplying by P. This is the per passenger part. Do I have space for this? Okay. But it's not just this, right? Because this $5 per passenger figure was applied for as many passengers as we have in excess of 81 or beyond 81. Okay, so we multiply by that as well, the number of passengers beyond 81. So that's the number of passengers, subtract 81 from that number. So that's this. This is the number of passengers in excess of 81. So if I have one more person than 81, that would be 82 passengers. Well, then we would have a refund of $5 per person. But if I have two more, then we would have 83 passengers. So this part would be 2. And then this would be $5 per person times 2. All right. So let's simplify that. So it would be $10 per person, right? Okay. So 560p minus 5p squared. This will be a plus because double negative. I'm distributing the 5p times 81. Well, 5 times 81 is 405. So now let's write the squared term first. And we have some like terms here. They combine to plus 965p. Okay, so that part is, I think, a little tricky. That's why I wanted to walk through it carefully. But we now have our revenue function, the revenue that the flight takes in. Okay, we're trying to find the maximum revenue. In a sense, it could be nice to have more passengers because you have more paying customers, but you have this refund going into effect, and that's what makes this a challenging problem, is to figure out that balance. We want more customers, but we also don't want that refund to go out of control, so we need that perfect middle ground to maximize revenue. All right, so that was step 3. We're trying to maximize revenue, and we now have it as a function of just P. That's step 3. I think I said that, but that's step 3. Okay, step 4, find the domain. Well, this point here might be debatable, but we certainly won't have negative people on the flight. So 0 is our low point. But with P being our variable, of course, there is a limited number of seats on the plane, but that's not given to us. We don't know that. So I would just say infinite. Perhaps you could throw in more planes. Of course, this isn't very realistic, but we don't have a firm number. So we just have to pretend it's infinite. So we're not given a clear cap, and therefore I can't really make this a closed interval. Now, what this means is that I cannot use extreme value theorem because this is not a closed interval. So we can't use extreme value theorem. And that means that it's not guaranteed ahead of time that we have an absolute maximum. So what I'll say here is we have to check. It looks like two C's. We have to check for a maximum. Once we have our critical points, we'll want to use first or second derivative test. And I'll use second. As we'll see, it's not too bad. Okay, so now for finding our critical numbers, what we could technically say 0, since it's sort of an endpoint, but that's obviously not going to maximize our revenue, having 0 passengers. So we'll do the derivative approach, taking the derivative of this function up here. Well, that'll always be defined, certainly. So we just look for the type of critical point where the derivative is 0. So 10p equals 965 divided by 10. Interesting how this isn't a whole number. In the end, we'll just round. So this will probably be our answer, but we need to do a test to make certain that this is a maximum, because I really can't use extreme value theorem here. So for all we know, this critical point could be a minimum. It certainly won't be, but in theory, that could happen. We just have to check. So we check for a maximum using the second derivative test. Remember, that test only applies to the type of critical point where the derivative is 0. Well, we certainly have that here. That's what we did. So we can use this. And it's really nice because when you take the derivative of this, you just get -10. While we're at it, I want to show off some new notation for the second derivative. So this would be taking the derivative with respect to p of the derivative, dr dp. And there's some notation I haven't showed you yet. We get d squared r over dp squared. So all this is new notation. So am I literally squaring dp? No. But this is helpful notation. Am I literally squaring d? No. And the reason this 2's in a funny place is when you can see it when you write it this way. I've got like 2 d's and 1 r, but 2 dp's down here. So we write it as dp squared. So again, it's not like I'm actually squaring these things, but it's helpful notation for the second derivative. Okay, that's just a little aside. It's -10. Quickly see that by taking this derivative here. Just have -10. No matter what p is. So that means the whole function r is concave down. And that means that when we have a critical point where the derivative is 0, like at this one, then it's a high point. It's a maximum. So, good. This is indeed a maximum. That's what we're looking for. Now, let's just be careful at the end here. What is the question asking? So we're asking, in this case, not for the maximum revenue itself, but the number of passengers, which gives the maximum revenue. So I'm not giving R as my answer, but rather the P that leads to the greatest R. And that's this right here. But let's round because you can't have half a person. So we round up to 97. 97 passengers will give for the maximum revenue. And 95 will probably be the same as that, I imagine, but we just had to round to something. So if we, yeah, that's, or they might be slightly different. I'm not sure, but doesn't matter too much. All right, so let's say we have 98 passengers. Well, it's great that there's an extra paying customer, but we have that refund baked in to where it won't really be very profitable for us to have that many because we're giving out so much in refunds. So this is that balance that works out best. For the airline, that is. Okay. Let's do another quick problem with the time we have left. So I made this one up. It's not very realistic, I don't think. But let's say the cost in dollars, not going to be too important for this, of producing X jars of homemade jam. My grandmother used to do this a lot when they had these farmers markets. So just reminded me of her. These homemade jars, or excuse me, these jars of homemade jams. We have a cost function for this, and I just made this up. But let's pretend it's real. Plus 4. Okay, let's say it gets a little complicated and we're looking for, what we're looking for is to minimize this cost. I haven't said that yet, but that's going to be the goal. We haven't done a minimizing problem yet. So here's the cost, and let's find the number of jars. We can produce to minimize cost. And let's just throw in a little bit, which will give us our domain, because we're pretty limited, let's say. So our options, excuse me, are between 1 jar and a dozen. So we only have a dozen we can possibly do. And well, we want to do one, otherwise, of course, you would minimize cost by doing nothing, generally speaking. That's actually not how this formula works exactly, but that's why I avoided the 0 case, actually. So 1 jar is our minimum, and our maximum is a dozen. So right away, that gives us our domain. Closed interval from 1 to 12. Okay. We're not going to bother drawing a picture. Again, that doesn't really help in these financial problems so much. More like the geometry where you're trying to maximize area or something like that. So, and there aren't a whole lot of variables involved here either. You just have X, the number of jars, and the cost. So the cost was given, and we will want to find our critical points. So actually here, that's step 3 already given to us as well, right? So we didn't have to do a whole lot of setting up for this one. Now we want to find the critical numbers. Those would be the endpoints, and wherever c prime of x is 0 or undefined. Right, so c prime, this plus 4 up here won't make a difference with the derivative. And let's factor out this -7 off to the side. So we're mainly focusing on this part, the x minus 1 times the e part. So first times the derivative of the second. The derivative of e to the negative x minus 1 is itself, but times the derivative of that exponent part. This is chain rule. So times the -1. But I'm doing this within a product rule. So I did the first part times derivative of the second. And now derivative of the first. The derivative of x minus 1 is just 1 times the e part left alone. Okay. So I'm just writing this negative over here. And just not writing the times 1. Don't really need to do that. Notice I can factor out the e part. It's in both terms. Okay, so we'll have -7 times e to the negative x minus 1 times, we'll still have this negative of x minus 1 left. How about I go ahead and distribute that negative? So that'll be a negative x plus 1. And remember, we had this term here. I factored out the e part, but that means there'll still be a plus 1 there. So negative x plus 2. Okay, this is pretty well factored. Don't necessarily have to do this step, but this will look a little nicer if I factor out a negative. Then it'll just be x minus 2. We like that. So I'm going to factor a negative out of here, and that will clash with this negative to form a positive. So just an x minus 2. That's the cleanest way to write it. Okay. Will this ever be undefined? That's the question. Well, it helps to know a thing or two about e to any power. It's always going to be perfectly well defined. And in fact, it'll also always be positive. So I'm just going to say it's greater than 0, no matter what I plug in for x. So that's also helpful for when we set this equal to 0. I know that this e part won't really make any difference with that, because it'll always be a number bigger than 0. So really what matters is this x minus 2 part. So that is our special critical number. And don't forget the endpoints as well. So we said 1 jar is the minimum number of jars we could make. Then 2 jars is something to look for. And a dozen is the maximum that we have lying around. So out of these, which will minimize our cost? Well, extreme value theorem applies here because our cost is a continuous function on a closed interval. So that means on this interval, I'm guaranteed to have an absolute minimum somewhere. So that means what's going to be at one of these places. It has to. So we just compare and see which gives us the smallest cost. And that'll be the smallest for the whole interval. Okay, so I plugged these in ahead of time. You get exactly $4 with one, and you get about $3.65 with 2 jars. And well, you get something very close to $4 with a dozen jars. So we have a clear winner. We're trying to minimize cost. So this is our absolute minimum on our interval. Now, as we finish the problem, what was it asking specifically? We'll find the number of jars. So that would be the x. So 2 jars. All right, well, we will have a little break. We won't have a lecture video for this Friday because of the upcoming exam. So spend your time preparing for that. Make sure you get your appointment, and I'll see you in about a week.